Hello everyone, this is the project presentation by Group 15, Daydreamers. I am Bowen Ma and my teammates are Shun Zhang, Yichen Wang, and Yuwen Cai. Our group project is called Decoder. This is our
Hi, I'm Yuwen, and I'm first introduce our decoder method, which is used in the entire system. So we designed a unique encoding method, which is different from the Morse code, but in very similar design. So we use our special the encoding like it seems similar to the binary code, but we have a 5-bit encoding method. So for 0, we have 50. And for 2, which is different from the binary result, we have 10001. 7, we have 1111, which is extremely different from the binary result and the Morse code. So this is why it makes our decoder different from others.
Okay, so after understanding the concept of our decoder and how that works, I will show you the main module of our program. As you can see here, it consists of two parts, the calculation part and the output part. So our division of work is fairly simple. Yuwen Cai and I made the input and the main ALU part, and Shun Zhang and Yichen Wang are in charge of the output portion. Our project may be a little bit different from our presentation, so we fixed the input to be 23-bit. As you can see here, we have 20 bits for two-digit numbers and 3 bits for the operation. And the output is shown by LED, which is kind of a way of encryption. And as you can see here, uh, it costs two parts of the ALU main module and also the LED long module. Next, I will just show the test bench for our passcoder. This is the test bench of our passcoder. So here, we just do one test each round, which is matched with our design. And also in here, we just try to uh, input the 79, and then we choose the operation to be times, which is multiply, and we want to time that with 98. And supposedly we have a result of 7,742, and I will show you the waveform that we have, which is right here. So in our waveform, it has two kind of blinks. So it has a long blink and a short blink. This one is a long blink, and as you can see, the time of high is longer, and here it's shorter. So in each section, we have high frequency blinks shows the end of the section, and in here, our result is supposed to be 7742. And if you can remember from the first part of our decoder that this part is 7, 7 is 1, 1, 1, 1, 1, and the next 7 is the same from the first one. And our 4 is 0, 1, 0, 1, 0. So short, long, short, long, short. And the same for the last part, which is the 2 part. 2 is 1, 0, 0, 0, 1, long, short, 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 long. And next up, I will show our calculation ALU part. This is the main code of the ALU part. And as you can see that it accepts exactly the same input as the main module. And the output of that is the number after calculation represented in the encryption form. There are 3 modules called in the complete ALU part, which is the calculation ALU, and the converter and the encoder, which makes a process of calculating the corresponding operation, convert the number into decimal form, and then encode the transferred decimal result into the encryption form. And I will next up show our ALUM test bench. As you can see that we test all of the 5 operations, the plus, minus, multiply, divide, and the power. So next up, I will show our simulation for the. So here is the waveform of our test bench for the ALUM part. So the first operation we did is 1 plus 2, and that result in a 3, which is in the encrypted form 10010. And the same case here for the next 4 operations, we have 57 minus 25, that equals 32. So we do not have anything in the thousands and hundreds digit. So we only have a 3 in the tens digit and a 2 in the ones digit. The same case here. We have 79 times 98 and 95 divided by 2. Here it's 9 raised to the power of 3. So that equals 729. And next up, continue to.
In this module, we will receive a 14-bit number, which is the output of the calculation after ALU. And then, in this module, we'll separate each decimal by simply using calculations in Verilog. We find that the divide only output the integer part, so in this way, we can separate the integer into 4 decimals.
Okay, so for the next part, we'll introduce our ALU decoder, which first we will have the full decoder here. Just like the Ripple carry adder, we use the same method for decoder. We use the simple decoder to decode a 4-bit decoder. So for here, we have decoder 1, decoder 2, decoder 3, and decoder 4. And then we have the number result. And from the number result, we do the ALU calculation, which is here. We have our add, subtraction, multiplication, and divide, division, and power. And same as the simulation Bowen just showed, all the calculation methods succeeded in the end. And this is how our decoder and the ALU computation method works. For the decoder here, the number result we first get is actually not the same, the result we want. So as you can see here, we use the PRE, which is the presentation. So in the simulation, we use the 7 to 2, but actually 7 and 2 is not the number that the user wished to input. The input actually is 4 and 8, because we are using our unique encoding method so by using the binary result which the system uses default, it is 7, but actually in our encoding method is 4. So this makes the number presentation a little bit different. But here we assign a number 1 and number 2 to make it readable and understandable for in decimal form.
In this module, we will have 4 input signals representing long and short lights. And before we reaching the final module, we have 2 failures. For the first one,
okay, for this function, we want to write a for loop like in other computer language, like C++. So this part is our first try, which fails. We want to set the counter to turn on and off in a period of 20. However, when we bring a for loop inside the always block, we find that it goes too fast and the counter will not even for 1 time before the for loop have already repeated itself for several times. So this is our first failure.
And for our second one, we try to list all of pointers we needed to set the LED light on or off in advance. It is like this way. And if the signal is equal to 1 or 0, then when counters reach the specified pointer, it will change its output, but it will be too complicated and long, although it should be right. Thus, we consider the third way to simplify it.
Okay, and as for this one, it's like a combination of the first two. We still use the idea of a for loop to control the time of the LED blinking. We set num1 to 4 to set 4 key points for our blinking, and instead of keep counter adding up, we reset it back to 0 each 20 period. Inside our always block, integer I serves as an index in the for loop and starts from 4, which is the leftmost digit of the input array. So inside the always block, if the index num is 0, we set a short blink in the period, which is set the LED on at 2 and off at 0 and end at 20. If the index number is 1, we set a long blink, which set the LED on at 2 and off at 12 and end at 20. With the index reduced to -1, we start the blink.
So if we don't have this I equals -1, I will keep decreasing and the program will not stop. So we add this if I equals -1 because in the previous if language, if counter is equal to number 4, I is -1. And in this case, when I is equal to -1, we get into blink process. We let LED signal changes when counter has an interval of 1, and then after that, we set I to be equal to -2, and then we go into the second signal. And in this one, we introduce another index called J. So we'll repeat what we did for I, and then we did it again for K and for X, and these are 4 indexes for our program. And this is our main program of the LED output.
Okay, so this is our demo for our LED output simulation. So we have 4 group of input. The first one is 0, 1, 0, 1, 1, and 0 here represents the short blink, and 1 represents the long blink. And group 2 is 1, 0, 1, 1, 0. 3 is 1, 0, 1, 0, 1. And the fourth group is 1, 0, 1, 1, 1. And we will start our simulation. Okay, and you can see in our simulation, the first group 0, 1, 0, 1, 1 is represented as the short, long, long for the LED blink for the first group. And then you can see several high frequency blink, which represents the end of this group. And second group is long, short, which represents the 1, 0, 1, 1, 0 for the input. And then after a blink, the third group, long, short, long. And after a blink, the last group, long, short, long. And after the last blink, the LED will remain off.
So finally, here is a block diagram of our full operating system. So in here we have the scratch from decoder, encoder, and then we progress our way into the full decoder, the converter, and the ALU calculator, and then the complete ALU, and we output that into the LED part, which made our complete passcoder. So this is basically our project. But one thing worth mentioning is that sadly our FPGA boards are still not working. It cannot be detected by the hardware manager, and our computer cannot connect it to it. So that makes our presentation so hard, and we use all of the simulation to do the work for us. But that is also one of the advantage I want to mention is that our system is completely working with the computer and exclude from the FPGA board. You can use it and use the LED or the 7-segment display to display our result, but it can also be used without an FPGA board, which is also making it more convenient. Thank you.